Hi, and welcome back to Blockchain Fundamentals with Bill Laboon. Today we're going to discuss the basics of cryptographic hashing. So, in order to understand cryptographic hashing, first we need to understand what a hash function is. So a hash function simply accepts some arbitrary input x, so some value or sequence of characters, a string, etc., and returns a fixed length digest or summary value. So, as an example of a hash function, we're going to look at something called BadHash. So as its name implies, you probably don't want to use BadHash for anything important, but it will let you understand and see what exactly a hash function does at a very simple level. So what BadHash is going to do is, given some string, some sequence of characters, it's going to convert all of those characters to their ASCII values, sum up those values, and return the result of that sum modulo 256. So this means that since it's modulo 256, we will get a value between 0 and 255 inclusive, or in hexadecimal, OXO through OXFF. So again, if you're considering using BadHash as an official hashing function for anything that you want to do, take a check at the name. It is not something you want to use professionally. So if you're interested, here's the code for BadHash. It's in Ruby. It simply accepts the argument from the command line, converts all of the characters to their ASCII values, sums them up, and returns the result modulo 256, and prints it out hexadecimal. So here we can see the hash of Bill is A3. So I get some value back from this string of characters. The hash of Bob is 33, of Barbara is CB, and Belinda is CF. So one thing to notice here, no matter the length of the string, I am always going to get a number between 0 and 255, between OXO and OXFF, whenever I run this hash function, no matter how long the input sequence is. So hash values are used for a lot of different things in computer science. So you've probably heard of the data structure, a hash map, which determines where to place some data in memory based on the hash of that data. Nearest neighbor search. We're distributing data in a ring or on a cluster. Where should we put this data? Where should this data be stored? There are a lot of different hash functions out there, all of which have different properties and things that they're useful for or not useful for. In terms of blockchain technology, we're most often interested in using hash functions for cryptographic hashes, as you might expect from the name cryptocurrency. So cryptographic hashes are hash functions that have the following properties. One, they are collision-free, or as we'll see, collision-resistant. They're hiding, and they're puzzle-friendly. So we're going to discuss what each of these mean, and as well as see why BadHash does not in fact meet any of these requirements for a cryptographic hash function. So, collision-free. For a hash function, h of x, it should be computationally infeasible to find a collision. That is, some y where x is not y, but h of x is equal to h of y. That is, if I have some hash value, then it should be very difficult for someone to create that same hash value using a different input string. So here, for instance, again, BadHash is bad. And why? Well, it allows for collisions. So here we use the attack at dawn message, and we want to verify that this is the message we sent. So we were able to say that the hash of the message that I sent you is 77 hex. So I then get a message that says, sit down, pound, 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 meow. And I say, well, the hash matches, right? So this must be the message that I was expected to get. So I sit down and meow instead of attacking at dawn. Why did I think this? Because it did have the valid hash value. But this bad hash is not collision resistant. In fact, it's very bad at collisions. It's very easy to create so I went back one slide there. It's very easy to create a different message that has the same hash value. There are only 256 possible hash values to have, so you can imagine that would be relatively simple, even from a brute force perspective, to create a message that has the same hash value as the original message. So remember I said we would like our hash function to be collision-free, but it turns out, if you think about this for a few moments, this is impossible. Why? Because we have an infinite number of possible strings that could be passed into the function. But there are only a finite number of hash values because it's only a certain number of bits. Remember, even with BadHash, no matter what the size of the input, we always had a 1 byte value between 0 and 255 resulting. Since we're mapping from an infinite domain to a finite codomain, we're going to have collisions, potentially. In fact, according to this, we will have an infinite number of possible collisions. So while we would like to have a collision-free hash function, usually what we say is collision resistant. But even if collisions are technically possible, can they be found in some reasonable amount of time? So if the size of your hash value is large enough and you have a properly constructed function that generates hashes what seem to be randomly, or what looks like random, even if it's not actually random, let's say you have a 256-bit hash function. That means that you would need to try 2 to the 256th possible values in order to try to match that hash value. Now, this assumes that there's no shortcut to calculating the hash. With BadHash, there certainly is a shortcut. We know if we want to increment the hash value, we just have to add some characters at the end, because that will increase the size of the hash. If we want to decrement it, we can decrease. Okay? So here we have a shortcut in BadHash. Since we know, remember, we're just taking the sum of all of the values of the characters in the input string. If we add more characters, we're going to increase the hash value. And then we can just keep adding characters until we get to the hash value that we want. A cryptographic hash function should be collision resistant. It should not have that shortcut in it. Okay? So there are holes that have been found in hash functions in the past. So a lot of these hash functions are considered broken for cryptographic purposes. That doesn't mean that they can't be used for other purposes. So for instance, if you ever look at the SHA on a GitHub commit, that actually uses SHA-1, which does have some vulnerabilities from a cryptographic perspective, but it's perfectly fine to use for simply keeping track of commits on your branches on GitHub. No hash function has ever been proven to not have any weaknesses. So while we do use a lot of hash functions in the cryptographic and blockchain world, that doesn't mean that these have been 100% proven, do not have any possible holes in them, but rather a lot of smart people have looked at this and they haven't found any issues yet. So we're going to at least trust them somewhat until someone does find an issue. So remember I said it will be very simple to find a collision with BadHash. Again, so we can see BadHash, not a good cryptographic hash function. We know that if we modify the characters, we know exactly how that will impact the resulting output. So if I change A, capital A, to a capital B, for instance, that is one letter higher, so thus one value, one increment higher, than before, so my hash value will simply be incremented by 1. We also are vulnerable to brute force because we only have 256 possible hash values. So, cut that for a second, sorry. So BadHash is not a good collision-resistant hash function. We certainly do not want to use it as a cryptographic hash. So we can also use a hash to prove what we said. So if h of x is equal to h of y, and we are collision-resistant, we can be reasonably certain that x equals y. So if we want to check that we have seen something before, for instance, we can just store its hash instead of the actual value. And since the actual value can be of arbitrary length, whereas the hash will always be of a certain size, you can imagine that this is very useful in places where you have a limited amount of memory, which is basically everywhere, but especially important on a blockchain where you have a limited amount of space because the blockchain is replicated amongst many different servers. Another aspect of a good cryptographic hash function is that it's hiding. That is, if I give you the result of a hash function, the hash value, h of x, it's infeasible for me to go backwards to determine what x is. So, in other words, h of x should be a one-way function, which we discussed briefly in the previous lecture. If our function, for example, h of x is equal to x plus 1, this is not hiding. It is very simple that if I tell you the result of this is 42, and you know the algorithm, it should be very easy for you to figure out that, oh, if I'm adding 1, to do the inverse, I just subtract 1. So here we have no hiding. Given h of x, it is trivial to find x. So that is a sort of a layman's understanding of hiding. The specific technical definition is that the hash function is hiding if, when a secret value r is chosen from a probability distribution that has high minimum entropy, then given the hash of r concatenated with x, it's infeasible to find x. So in other words, what this means is, if the value r is chosen uniformly, the result that we get from the hash value, it's likely to be any one of any of the possible output values. That is, adding some additional data onto this will not make it any easier for you to understand what the resulting value is. But I think the easiest way to understand this is going from the result, you can't go back to the initial input, or at least it's computationally infeasible to do so. So is BadHash hiding? No. Why? Because according to our technical definition, adding an additional character is really going to bias the direction that our resulting hash value is going to have. And looking at the characters, we know that any additional character is going to add on to that hash value, right? Because remember, we're just taking all the characters' values and summing them up. So if we add more characters, we can't have negative value characters, and so we know that it's going to increase the value. And modifying characters, well, we know that if I go from A to B, that's going to increment the final value by 1. So if I can actually, very simply, if I'm trying to get a similar hash value, I can modify the input until I get a hash that is equivalent. It's not hiding. It's very easy for me to go back and try to find something else that this data may have come from. Now, if we do have a good cryptographic hash function, we can use hiding to create what's called a commitment scheme. So let's assume you would like to wager on something, but you don't want others to know your guess. So an example might be the price of a Bitcoin will be over $10,000 in 1 year. And you want to be able to say to everybody that you predicted this in the future. Or you want to make a bet with your friends. but you don't want to reveal what your guess on something is. It may bias other people. So a commitment scheme will allow you to do this and later reveal what your message was and do it in a verifiable way. So the commitment scheme consists of two functions, commit and verify. So with commit, you take a message and add a nonce. So this is just some random value that can be used only once. So if you recall back to our technical hiding definition, this was the value R. We're going to see the term nonce used quite often in our exploration of Bitcoin and other blockchains. Just remember, it's just some value that it's a nonsense value. It doesn't mean anything on its own, but it can be used for different purposes by usually concatenating onto some other data. So if we assume that this commit function is hiding, I can commit a message and add a nonce to it, and it's going to be very difficult, computationally infeasible, i.e. basically impossible, for somebody to find some other message in nonce that hashes to that same committed value, that hash value. After I generate this hash, I publish it publicly, I let everybody know about it, and then later, everyone has already seen this value. It may be on the blockchain, it may be published in the newspaper, it may be posted on Twitter, whatever. You can open the envelope, that is, show what was written inside of this, that was represented by this hash, by publishing the nonce and the message. And then anyone can verify that the message concatenated with the nonce will give you that same hash value that you committed to. So let's just walk through an example with this commitment scheme. So you have a bet with your friend, or perhaps multiple friends, who will be the US president next year. But you don't want to declare it for whatever reason. You don't want to bias what your friends think or something like that. So you decide that the person that will be president is Bill Laboon, and you come up with a randomized or pseudo-random nonce, 73901292311. You then take a good hashing function, again, not BadHash, of the string Bill Laboon and then concatenated with your nonce. So this gives you a hash value, EB97 ... When you publicly announce this hash value, you're committing yourself to it. You will not be able to come up with some other string that hashes to that value. And hopefully no one else will be able to come up with some string that hashes to that value. When I say hopefully, I mean the odds against it are astronomically unlikely. It is also difficult for someone to try to figure out who your guess is, assuming you've picked a large nonce. Because if there are only a few people who might potentially be president, then you could try each of their names in turn until you figure out what it hashes to. By adding this additional nonce, you have made that much, much more difficult. So hopefully the only one who is going to be able to, in all practicality, reveal what this hash was hiding is you, assuming you store your guess and the nonce. So when, of course, Bill Laboon wins, and you are going to prove to everyone that you knew it, you can reveal the string and the nonce. So you can say Bill Laboon 739 ... and then check what is the SHA-256 hash of Bill Laboon concatenated with that nonce. And if it equals the hash value that you have already committed to earlier, everyone will know that you did in fact call Bill Laboon to be president, even though you never had to publicly state it until it actually happened. So the last aspect that makes a hash a good cryptographic hash is that, and especially for Bitcoin and other proof-of-work blockchains, is that it's puzzle-friendly. That is, for every possible output value of n bits, if k is chosen from a distribution, again, so a high min-entropy distribution, it's infeasible to find x such that k concatenated with x equals y in time significantly less than 2 to the nth. So kind of a complicated definition, but really all it means is that there are no shortcuts. If someone wants to produce the hash value, some particular hash value, if h of x produces a result of size n bits, then they're going to require at least 2 to the n attempts. In other words, the best way to find the result of a hash function is simply to try it. There are no shortcuts. So if you want to find something, for example, a hash that starts with a 0, then the best way to do that is to keep trying different hash inputs, running it through the hash function, and seeing what results. There's no shortcut to say, oh right, if I have the letter A in my hash, I'll always have a 0 at the beginning, or I'm more likely to have a 0 at the beginning. So puzzle friendliness comes in handy with proof of work, because if you want to prove to somebody that you have done work in order to get a prize, like generating a Bitcoin block, you're going to be asked to find the value of a hash that is below a certain number. And the easiest way to do this is just going to be running lots of different possibilities until you get a hash result that meets these requirements. There are no shortcuts. You just need to try lots and lots of different possibilities. Is BadHash puzzle friendly? Definitely not. It's very easy to determine the output and then modify the input that will modify the output in deterministic and easy to follow ways. So remember, I'm trying to generate some hash value that is 0, 0. Some input that will give me the hash value 0, 0. So I start with AAAA and I get 0, 4. So I then know that if I modify my characters, that I'll be able to modify the hash in certain deterministic and easy to follow ways. So I change that last A to a lower ASCII value character, the less than character, and I see, oh, right, that's FF. But I know, since we use modular arithmetic, if I just add one more value, increment that by 1, then I will get 0. So here I messed up. I did a question mark that was a little bit higher. So I know that or what happens if I subtract 2 from that? I get the equal sign. So AAA equals gives me a hash of 0, 0. I obviously could have made this even shorter if I just had an ASCII table and I could calculate it out instead of trying to remember where the particular ASCII values of different characters. So we can see this is problematic because I don't have to try on the order of 2 to the n. This is 2 to the 8th, so I should have to try on average about 128 different possible values before I get something that's hashes to 0, 0. So we can see BadHash did not meet any of our requirements for a hash function, a good cryptographic hash function. It's certainly not puzzle friendly, it's not hiding, and it's not collision resistant. There are a few hash functions used in Bitcoin, and there are a lot of variations of these used on other blockchain technologies. SHA-256 and RIPE-MD 160 are both used very often for different purposes in Bitcoin. All of these are good cryptographic hash functions that don't have any major known vulnerabilities. We'll use SHA-256 as an example for a lot of our different hash functions here, as it is a good and well-known cryptographic hash function. It is collision resistant, it is hiding, and it is puzzle friendly. It produces output of 256 bits. So you can see here, for instance, a hash of AAAA is 63C ... And unlike BadHash, look at the next hash function result, AAA less than sign. This changes the result of the output dramatically. It's not just moved up or down a little bit. It is changed very dramatically. Even going from AAA to AAAB gives you a large amount of modification in the output data here. So on average, for a perfect hash function really would modify approximately 50% of all the bits in the output based on every bit that has been changed in the input. So that concludes our lecture on hashing. In the next lecture, we'll take these concepts we've learned on cryptographic hashing and apply them to data structures and actually start generating a blockchain.